everyone. Thanks so much for joining today's session. I'm Melissa Everett, Executive Director of Sustainable Hudson Valley. Our mission is to find new and more impactful ways to tackle the climate crisis. And our sweet spot is where the imperatives for action connect with creativity. So we're the people who have brought you the Solarize campaign, electric vehicle ride and drives, and most recently the regional climate action roadmap and toolkit to create more of a common vision. We are all in for scaling up renewable energy. Right now, we're working to press our utility for dialogue on making the electric grid planning process work better for towns. At the same time, looking at the pace of climate change and the concentration of greenhouse gases in the atmosphere, we are highly motivated to understand the emerging field of carbon dioxide removal. So we are thrilled to bring you experts and advocates of wide range and deep roots in this work. Through regional planning work, we met Chris Neidl, who will be kicking us off with the overview presentation. Chris is the advocacy director at Rethinking Removals, a carbon removal focused think and do tank based in London. He's also the co-founder of OpenAir, an all volunteer advocacy and citizen science network advancing carbon removal all over the world through member activities. Prior to shifting to carbon removal 5 years ago, Chris spent 15 years in the solar industry internationally. A proud Albany native and longtime Brooklyn resident, he currently calls Austin, Texas home. Through family connections, I've gotten to know Lila Connors, founder of Catching Carbon and director of Tree Media, a very impactful think tank and media production business with a powerful body of work on climate and other global issues. Lila has been doing independent investigation of carbon dioxide removal with experts and innovators since 2002. She's based in Chatham, New York, where she's active in the local Climate Smart Community Initiative. So Chris will kick us off with a presentation and introduce our expert panel. Then Lila will facilitate the question and answers and discussion. Please discover the chat box, introduce yourself, and put your questions there at any point. And yes, we are recording. Thank you for joining. Chris?
Excellent. I'm thrilled to be here. Again, just a sneak peek of what comes after my short, around 20-minute or less presentation is that Lila will be convening that excellent conversation with some CDR practitioners that are mostly local. So looking forward to that half of the program. So as Melissa just said, I want to really keep this pretty high level and really give people some concepts, some vocabulary, and a kind of a framework to think about carbon removal, which you might have been hearing about lately. It's a very complicated subject. So I want to give you enough to feel that you kind of understand the shape of it. And then we'll get into the panel where we'll go a little bit deeper. One thing I'll say too is there's not a Q&A box for this meeting, but you can use the chat. If you have questions, go ahead and put those in there and we'll actually fold that into the panel discussion. So again, just two very complicated subjects. So I'm going to hit some pretty high altitude here and then we'll get a little bit deeper. What I want to do again is start with some just basic definitions and terms. And then importantly, first talk quickly about what carbon removals is not, because this is so new. There's some confusion about some sort of big things about what is carbon removal. So we want to clarify those. And then I'll get into a series of definitional points around what carbon removal is, why is it important? And then we'll end by giving you a little bit of a sense of how do we compare carbon removal or make choices between the many different options that there are when it comes to actual implementation. And so just to start with the very basics, this is a definition that comes from a paper written by Dr. Jennifer Wilcox. She's currently the Carbon Management Director at the U.S. Department of Energy. And carbon removal, as it sounds, are activities that take carbon out of the air and they put it somewhere where it's going to stay out of the air, whether in geological structures or terrestrial, ocean reservoirs, and also in products. Some other terms that you'll hear if you hang around the carbon removal space that are synonymous, more or less, are carbon dioxide removal, or CDR. That's probably the most common. Greenhouse gas removal, or GGR. That's more common in the United Kingdom and the Pacific Northwest. It's a more inclusive term that talks about removing other forms of greenhouse gases in addition to carbon. And then negative emissions or negative emissions technologies, NETs. So you'll often hear those used interchangeably for the most part. And another really important concept that's not a synonym for carbon removal, but an aim of it that really motivates our community is the idea of climate restoration, that this is a set of solutions can ultimately help us undo some of the damage that we've already done, because as we know, we're already in dangerous territory and where we are right now in terms of carbon concentrations in the atmosphere. And so let's go ahead again and start with what carbon removal is not. Okay, so one critical thing that our mantra to repeat again and again and again is that carbon removal done right and in a science-aligned way is not a substitute for rapidly and as aggressively as possible eliminating or reducing emissions, or for making necessary adaptations or investments in adaptation. It's a third thing that we now have to do, and I'll explain that shortly. And so what we try to say, just our sort of stand-in annoying, arrogant person picture here, is that if someone tells you, and you will hear this, there are messages that, well, we can just do carbon removal later instead of reducing or emissions or adaptation. That is fundamentally wrong. And so that is something that we try to resist in very powerful ways. So that is not the argument that we're making here today. Carbon removal is also not carbon capture or carbon capture and sequestration. There's often a lot of confusion, and part of that is because the word capture sometimes is used in carbon removal. But carbon capture is actually a form of reduction. This is, regardless of what you think about it, this is where you stop emissions going up from industrial point sources and then putting that carbon somewhere. Carbon removal is taking carbon that's already in the air out of the air. And they're different technically, and there's different rationales and reasons for pursuing either one, but they're not the same thing. Now, what is carbon removal? The main thing to kind of drive home, I think today, if nothing else, is that it's necessary. That's really what's brought us all together. It's not a nice to have or a substitute for something else. It's a necessary part of our ability to address the climate emergency. And the reason why that is that many of us know is we move too slowly. In some ways, the ship has already sailed, where we can no longer contemplate maintaining a livable temperature change without carbon removal. And where does this come from? This is not controversial in terms of the scientific community. The United Nations Intergovernmental Panel on Climate Change has now for a number of years, in increasingly strenuous terms, made clear that we're going to have to take carbon out of the air, and lots of it, up to 100 to 1,000 billion tons over the course of this century. And that's a lot. It sounds like a lot, and it is a lot. It's in the shorter term, it's necessary to counter some of those industries that are just incredibly hard to transition in a climate meaningful timeframe, such as industry, transport, and agriculture. And then in the longer term, this is from the most recent IPCC report, is that we have to get to net negative. We've already really been overshooting. And so if we're going to do that, the way that we have to do that is to scrub carbon from the air that's already up there. And so this is a very famous, well-circulated graph from the IPCC that kind of shows that visually. And so you can see above this blue line, this is all the really aggressive stuff we have to do to reduce emissions. But below that, there's this other part, and these are the negative emissions, that this is what we have to do to ultimately get to net negative, is it has to be a combination of both near-term rapid decarbonization and then growing our carbon removal capacity as we get deeper into the century. Now, another thing that's really important is if you've encountered this, often carbon removal is sort of talked about in monolithic terms, that it's maybe just one thing or two things. One of the things that's just breathtaking about carbon removal is that it's an incredible spectrum, which you'll hear about today from our panel, of different types of totally dissimilar pathways. So there's many different ways in which we can do this, not one or two. And just categorically, we can do carbon removal on land. We can do it in very exciting ways involving the ocean. Some forms of carbon removal are large and centralized. Some are very, very distributed and small and happen over large space and timescales. One thing that's really, really important to address is that carbon removal is more than forests and soil. Now, obviously, we know that trees and forests take carbon. We can store a lot of carbon in soil, which is good for the soil, good for agricultural productivity. And these are inherently valuable when we wanted to do these anyway, even if there wasn't a carbon removal benefit. And this is for biodiversity and ecological reasons, as well as the economic services that come from forests. So that's something we have to do. But alone, we can't just depend on trees and soil because of the amount of carbon that we have to remove. In this graph that I showed before, has these two layers that represent the negative emissions or CDR part, those that are basically trees, soils, mangroves, peat, things that are unmanaged land, and then these other removals. And here you'll see that this really has to start ramping up over the next 15 years, in addition to what we can do with land-based carbon removal. And the National Academy of Sciences a few years ago had a 500-page paper, and their estimate was that about 40%, and that's reflected here in the IPCC data, will be able to come from nature-based solutions or working lands-based solutions, or rather from managed lands. Now, what about the remaining 60%? Now, where is that going to have to come from? And this goes by many different names, but one that you hear often are novel carbon removal. So these are sort of newer, emerging, or being rediscovered in some cases, that will have to fill out the difference. And so just to run through these again, you could slice this up and go into a lot of depth, but I just want to give you enough to kind of wrap your head around the subject. One we call durable biostorage, and this is like natural sinks. It removes carbon through photosynthesis and through the normal process, but it comes up with engineered ways in which that carbon, rather than when a tree dies or something gets disrupted, it gets re-released, that will make it store and stay out of the air for longer periods of time. Some examples of this that you'll actually hear about today from our panel are biochar, as well as burying trees, waste trees, and other biomass in vaults underground so that they don't decompose and release carbon dioxide. Taking algae, which loves to suck up carbon really, really quickly, and sinking it deeply to depths where it won't break down and be re-released. And then Becks and Bickers, we have one of the country's leading experts on that, Josh, joining us, and that's a more kind of engineered technology-focused approach, and he'll be getting into that during the panel. We also have CO2 mineralization, and this is basically turning CO2 that's gas in the air into a form of rock that won't go back up into the air, and it'll stay. And there's many different ways of doing that. Some you'll hear about today on the panel. Enhanced rock weathering and mine tailing mineralization. These are where you take certain types of rocks that just love to bond with carbon naturally, and they do, called ultramafic rocks, and you're able to spread or distribute them in ways that accelerate that process while also doing good for, in the case of enhanced rock weathering, agriculture. You have certain types of rocks that are underground where you can inject carbon into, like basalt, that's subsurface mineralization, and then really fancy technologies that use electrochemistry to achieve that as well. Then you have ocean alkalinity enhancement, or alkalinization, which is a really, really exciting emergent technology. And what this does is we already have too much acid in the oceans, we know, that's killing off the coral reefs and a lot of biodiversity in the ocean. So we want to reduce that. And so this adds pure alkalinity to the ocean to make it more basic, which has the deacidification effect, but that also allows the ocean to absorb more carbon from the air, because that alkalinity turns into carbonates that sink to the bottom of the ground. And there's different ways of doing that are really exciting. One thing is exciting here in New York. We have two companies that came out of New York that are real pioneers in this, or one is based in New York and the other one has piloted something on Long Island. So there's local activity happening in this area. And then last is direct air capture, which might be the most talked about and also in some ways the most controversial and I think misunderstood. And so direct air capture are machines that are purpose-built to chemically suck and absorb carbon out of the air and then put it somewhere. And so this is one project, the first commercial one in the world, about a year and a half ago, was commissioned in Iceland, called Orca, by the company Climeworks and another company called CarbFix. And this is really cool. It takes carbon out of the air. The energy that it uses is renewable geothermal, and then injects that carbon directly below it without a pipeline into some of that ultramafic basalt rock, where it turns into stone in like 2 or 3 years. But importantly, when you think this, which I showed before, DAC really needs to be understood that it happens in a lot of different ways. It's not one thing. It's many, many different things potentially. Some are large and centralized, some small and distributed. And it's almost useful to think about this the way that we think of like solar. You know, you could have large utility scale direct air capture. You could have more industrial scale. In a really exciting segment of direct air capture is building integrated, actually having direct air capture integrated into your building, removing air from the carbon from the indoor environment. It runs on different types of triggers. Some use heat, some use moisture, some use electricity, but these again keep expanding dramatically over time. Now, how do we compare carbon removal? How do we know what's good carbon removal? or what are the forms that are most beneficial or that we should really focus on. And before I kind of go into what we think is a practical way of looking at that, one thing is that you hear a lot in the sort of the discourse or debate around it is this idea of nature versus technology. We should do just nature, just technology. And that to us is sort of a mysterious way, for me at least, 5 years into carbon removal, of thinking about it. It seems when you really kind of poke at it, it can seem kind of arbitrary. And if we could do only nature-based in trees and soil, then that's cheap. That might be the best way to sort of pursue it. But because we can't, it's really likely to be a mix of different technologies. And many of the solutions are not one or the other. They're actually a mix, or they're a hybrid. They involve something that is biological and naturally occurring, but they enhance it. So, and it's also worth noting that this is not a standard that we use when we think of clean energy and storage. We don't insist that has to be nature-based. We expect in technical innovation to be part of that. The same for clean transportation. The same for efficiency and conservation, which is increasingly technology enabled. And also the same for adaptation. These are all things where we have an expectation that technology is going to play an important role. And we think that's the standard that really should apply to carbon removal as well. And just to give you one comparison, which is one that we think about a lot, carbon removal is a lot like, metaphorically, like cleaning up an oil spill. That's where there's oil has gone into the ocean, it's disrupting eco environments. We have too much carbon that's already in the air and it's disrupting our atmosphere. And again, with oil spills, we just go right now with what is the best options we have and continuously try to improve on those, which involve a lot of technology. And that continues to evolve. There's robots and microbiology engineering that is making that better and better. But again, the important thing is we don't insist that it has to happen through purely quote unquote natural means. So we base it instead on how good is it at doing the job with the least risk or efficacy. And so when you think about efficacy, or how do you evaluate whether it's good carbon removal or worthy of investment, there's a number of different ways that we think about it. And these 7 here I've listed, and I'm only going to just say what they are without explaining them because it'll come up during the panel. But the first is scale. How much carbon, if we max out the potential of this on the planet, could it take out of the air relative to how much we have to take out of the air? So what's its future scale potential? Cost. We have to get this a lot cheaper in most cases. What is the net cost of installing and operating and maintaining these solutions? But importantly, right now and tomorrow, because we know that a lot of these technologies, just like solar and wind and batteries, they get cheaper over time as they scale. So what can we sort of think about in terms of cost related to particular solutions? Speed. That means both, is it ready to go right now? Sometimes that's called technology readiness level, or TRL. Like, when can we start going on this? And then there's the question of, well, even if it's ready, how long does it take to stand up? Is it like a big power plant that might take 10 years to plan, or you do it in a week? So these are important factors. Verifiability, really, really important. How do we know it actually happened? What methods are in place to demonstrate that carbon removal occurred, carbon storage occurred, and then it's going to stay that way for the period of time in which it's supposed to? So this is a hugely important part of carbon removal. Durability. How many years does the carbon stay removed once it's been taken out? Is it decades, centuries, millennia, forever? And importantly, on the flip side of that, is it easily reversed? Can we count on it staying where it's supposed to stay, or can it leak out, or can it be in some ways reversed? And then finally, or second to finally, resource needs. So how much land or energy or water or other inputs does it require? Is that sustainable? What's the net carbon footprint? And how can that change over time based on innovation? And then last, and certainly not least, that's why I'm putting it last, is what other things can it do that might be beneficial, and what potential risks have to get mitigated against, right? So does it create jobs, or does it create other products? Does it restore ecosystems, or does it potentially pose threats to those things? So these are all the different dynamics that you want to look at when you're thinking about selecting for carbon removal now and in the future. And I won't get into this, but I can drop a link. But if you kind of just look at different CDR pathways, there's vast differences. You might have direct air capture could be, has a huge potential to, remove 40 gigatons per year of carbon compared to, let's say enhanced rock weathering and biochar. But biochar is really, really cheap and it can be done really, really quickly. So they all have different advantages to each other. And so I'll skip through these slides here to avoid brain damage. And then just a couple of last points is, carbon removal is fairness on a global level. It is the sort of, I think, sort of the most emblematic of climate justice. And this is becoming part of the discourse that you're hearing from the global South. And this quote is really quite interesting from the Indian Minister of Energy and Power a couple of years ago, is that they're saying, the developed countries in the North put all of the carbon into the air and they've crowded out our ability to emit. So we need to not just be talking about net zero among wealthy countries, they need to be taking carbon out of the air. And some countries are listening. Finland was the first country last year to pass a net negative commitment, and a lot of it was based on this very argument that you see. Carbon removal is also an opportunity. So if we accept on a policy level that carbon removal has to happen, that means it's going to become a feature of national and state commitments. And that is, somebody's going to have to do it. And so it's estimated by many different sources that we're looking at a future $1 trillion industry. So this is something that can actually create economic value, not just be a cost. And then last, it's urgent. And this is really, really important. We can't just turn on carbon removal in the middle of the century from scratch. Okay. Just like with renewables and other sources, it takes time to get these things ready. It takes decades. And again, we've seen this with renewables, with batteries, is that it's a multi-decade thing. We need to do it quicker with carbon removal, right? So we need to start now. And this graph, which I showed you before, also shows, well, when does that have to happen? Right now is the time for massively scaling up renewable energies, electric vehicles, things that we call decarbonization. That's a major investment. We have to get to that point as we get deeper into the century. But right now, during these critical 2 decades, we have to be improving the technology, commercializing it, getting out and reducing the costs. And that's our mission right now. And this also brings up one other thing that people often are concerned about is, well, don't we have to spend everything on decarbonization? The reality is, to get to where we have to with carbon removal, because of the kinds of investments we need to make right now, which are similar to where we were with renewable energy a generation ago, it's less resources that are required right now compared to decarbonization. So these can both coexist together fiscally. All right. And now I will pass over to the panel, because this leads to the question, well, where can this happen and who will do it? And one of the things hopefully you picked up is that we have so many different forms of carbon removal that can happen in different places. And wherever you take carbon out of the air, anywhere in the world is beneficial. So it can happen anywhere in the world. But we like people to really think about, what does that mean for where I am? And so what we have today with Lila and with our panel is the ability to kind of talk about some of the issues that I just raised, but then to also start to talk about what are some things that actually might be able to happen here. And so what I will do, I can't look at both at the same time, I realize, so I'm going to kind of wing it here. But Lila, who was introduced already by Melissa at the top, is one of the core members of people really trying to drive carbon removal as a storyteller and filmmaker. We'll drop her link. We have Deeta Chowdhury, who's a member of the Carbon Gardener Citizen Science Project, which is focused on enhanced rock weathering. Joins us from New York City, but going to Cornell next year. We have Bill Hilgendorf, who's with White Feather Farm. He's the director of sustainability and biochar based in Saugerties. So he's going to be talking about biochar. Josh Scheidel is one of the leading experts in the country on what is called Becker's bioenergy, or Beck's bioenergy carbon capture and storage, and he's going to tell us a little bit about that. And then we have Peter Oliver, who is the head of new markets for Undo, which is an amazing company based in Scotland, but with global scope. He's based in Hudson, and they're focused on enhanced rock weathering. So with that, I'm going to hand it over. I'll stop sharing my screen, and I'll hand it over to Lila.
Thanks, Chris. That was fantastic. And as he said, this is a massive, new and wonderful industry with a lot of detail. So I thought he did a great job, and I'm looking forward to pulling out some of the threads for this region. I'm actually doing a film on carbon removal. And what I've learned is that this nature versus tech argument also is really specific to long-term and short-term carbon removals. And when we're talking about 100-year cycles, it's nature. If we're trying to restore the atmosphere, it's thousands of years, putting it back to this long-term carbon pool that we've destroyed, burnt over the last 150 years. And that's really what Chris has just been reviewing, is those technologies are the things like DAC, like, burying, algae on the bottom of the ocean floor or other macroalgae. Those are the things we have to learn how to do. And it's fascinating. Biochar as well is a whole other world in which it can do a lot of things. And the last thing I'll say before moving to the panels, there's a lot of co-benefits. There's a lot of jobs It's a disruption of materials production, a way to generate energy. It's new ways of looking at industrialization and localization. So it's very exciting. And if you're interested from this panel, please look at OpenAir. They have a lot of, Melissa dropped the link in the chat, a lot of different weekly, webinars on this stuff. But in any case, we want to bring this to Hudson Valley, and this is why we're on this call. And first, I'm going to go to Bill. And Bill's the director of biochar at the White Feather Farm in Saugerties. So Bill, tell us why you're so excited about biochar and why, and what farm is doing it or planning to doing it. Tell us how this is, coming out here in Hudson Valley. I think you're on mute still.
Thank you, Lola. So I came to biochar I have a design background in industrial design and always working with looking at reclaimed and upcycled materials. And when I found out that there was this ability to make, to take this vast waste biomass that we have all around us in the forests of the Catskills, on the farm, it just really caught my eye, and is that we need to do something here. And so on the farm, we're able to, we're in a great position as we're a small nonprofit organic farm, but we are right next to a third generation lumber mill. And so we're able to work with them to utilize their massive amounts of waste from the milling operations to create a lot of biochar. And on the farm, we're working, mostly on soil, but also some pretty cool additional ways that we're utilizing it. So we're putting it directly, we're mixing the raw biochar in with our compost. So we're co-composting with it to inoculate it. And, for people who don't know a lot about biochar, it's kind of like this dry sponge, the huge surface area. So it just absorbs everything. It's great for, holding water, micronutrients, as well as being a home for microbiology and air, to help aerate the soil. So all these things that help create a healthy soil. So we're putting it, co-composting with it, but also we're putting it directly into the soil, subsoiling it using the broad fork to really get it into the soil and letting it inoculate in the soil on its own. We're also doing some sort of more experimental stuff. We're adding it to our chicken coops and the bedding as odor control, but also that bedding all goes into the compost. So it's another stage of that. And then we're also working on doing some water filtration systems with our pond to filter out some of the nutrients there, as well as collecting some of the runoff from our beds in these sort of biochar socks that we set up around to keep some of those nutrients, to get them into the biochar and then working them back into the soil.
And so for those that don't understand, can you do a brief sort of summary of what is biochar? And also for the Hudson Valley, because we have land.
Yeah.
So just before having gone around the world seeing, there's definitely certain CDR modalities that work better in some regions. And we're really ways in the Hudson Valley to do biochar. So what is biochar?
What's that?
What is biochar?
What is biochar? Yeah. So, I think another thing that really attracted me to biochar is it's so simple to make. It's, from everyone can be making it in their backyard to very high tech, large scale operations. But basically what you're doing is you're just taking waste biomass, whether it be from the forest, crop waste, cow manure, anything, any kind of biomass, and you're heating it up in a low oxygen environment, and you're driving off all the volatile gases, and you're basically reducing it just to carbon and whatever trace minerals were in that material. So you're able to basically sort of disrupt that carbon cycle where if a tree falls in the woods and no one does anything, most of that carbon returns to the air as carbon dioxide. But with biochar, you're able to heat it up and thermally convert that carbon to a stable form, which allows it to persist, if undisturbed in the soil for over 1,000 years. So it's a really, really simple way to take that waste material and turn it into a really valuable resource, not only for soil, but potentially to decarbonize building materials, consumer products. And then you also produce energy and heat when you make it, which can be utilized as a renewable source of energy.
Yeah, it's interesting that it can insert itself into waste streams. So converting waste streams to value. So you actually can create value from waste streams, and sometimes even leave the tree to decompose in the woods and feed the forest, but also just taking the trash from a town and turning it into char that could go maybe into concrete and things. So biochar, that's why we're doing a whole other movie just on biochar, because it's really kind of a magic substance that it can do a lot of things. But I think overall in the Hudson Valley, there's a lot of land, there's a lot of farms, and it's another way for farmers to also, improve the quality of their soil, actually also remove carbon, maybe have some carbon credits there, and it's another revenue stream for them. So I'm going to move on to enhanced weathering because we're just keeping in time, and then we'll circle back to you on biochar with more questions. And so now I'll bring in Peter. This is another exciting agriculturally based form. It's called enhanced rock weathering. Peter, you're part of the UNDO team, a leading innovator in the field. Your company is based in Scotland, I guess, and focusing on the global opportunities of ERW, but you're located in Hudson. Tell us why you focused on enhanced rock weathering. What are the advantages and how is it a little different from biochar? How do you see that fit in here in the Hudson Valley?
Sure. So first of all, thanks, Layla and Chris. It's really fun to get a chance to talk about. I usually spend a lot of time thinking about Scotland and wider US global operations. It's really fun to talk about the Hudson Valley where I live. So I think quickly, just how does enhanced rock weathering work? It's the physical and chemical breakdown of silicate rocks, which are a really common rock on the Earth's surface. That's called weathering, right? And that's a fundamental process that helps control atmospheric CO2 levels. And so over geologic timescales, natural weathering of volcanic rocks globally sequesters about 180 million tons of CO2 every year. And the way it does that is as rainwater falls through the atmosphere, it combines with CO2. So CO2 dissolves in the rainwater and forms a weak carbonic acid. When it hits volcanic rock, the rainwater interacts with the basaltic rock or volcanic rock, which contains calcium and magnesium bases. And so the carbonic acid and those calcium and magnesium bases generate a chemical reaction which stores carbon dioxide as a solid bicarbonate. And that's really long duration storage. So, 100,000 years plus. Practically, this looks like crushing up different, specific kinds of rock. There are lots of different kinds of rock you can use, but generally volcanic rock is kind of the right way of thinking about it. And spreading that out on cropland, and then thereby dramatically increasing the speed of the natural reaction, right? From shortening timescales from geologic time to human relevant time scales, about 20 to 50 years. So this is the kind of analogy that is useful here is making coffee. You grind up the beans that you use to make coffee so that you can make coffee in a few minutes and not over the course of, a couple of weeks. So we do this a very similar thing. We optimize the process that we're looking for, both from rock and also from the practical application of those rocks, so that we get a ability to remove carbon durably and at scale. So a couple of the advantages. First of all, this exists in the context that I think Chris laid out really well, but we need to get billions of tons of CO2 out of the atmosphere and keep it out permanently. The obvious problem is it's really hard in that billions of tons is just a lot of mass, right? And so it's hard to solve these kinds of things with software. One of the primary advantages of enhanced rock weathering is that it leverages two industries that already operate at billion-ton scale, namely the production and application of aggregates, so construction materials, and farming. So every year, more than 40 billion tons of crushed rock, sand, and gravel are used globally. And so in some sense, we already have the things that we need here: rock crushing, processing, loading, all the trucks and equipment that we would need to do this at real scale. And because we're really good at this and we've spent a lot of time on this, the weathering process the tools that we use are very carbon efficient. So for every 20 tons of carbon that we sequester, about 1 is released. So it's about 95% carbon efficient. And global cropland is about 1.7 billion hectares. And because you can apply enhanced rock weathering with existing infrastructure, tractors, spreaders, things like that, we cannot rely on farmers that already have the know-how of doing the work and often already have the equipment that they need. So you stitch together these two.
Sorry, go ahead.
Yeah, no, you stitch together these two bits, and it means that we can leverage the world's largest industries to scale carbon removal. And the estimates for potential for CDR via enhanced rock weathering is about 2 billion tons a year. So that's the kind of one side of it, is that you can actually do this work at scale enough to affect the climate. The other piece is that in the short term, working with enhanced rock weathering will be primarily defined by the co-benefits it delivers to the communities in which we operate. And so you can really get into supporting local communities. As I said, we use existing infrastructure and existing tools. That also means that we create jobs within existing industries, whether those be farming, driving, hauling, spreading. These are all things that people in the community can do now. And so we can create jobs in those communities. We also can, because we're paying people to do work, we deliver a lot of income back into communities. So for the, approximately 80% of the cost of doing our work goes into the communities in which we operate. Moreover, you see, so there's financial benefits to doing this work into the communities, and I think that has knock-on effects for the palatability of doing carbon removal at scale. I think you can also get into the soil benefits side and consequent farm benefits. So we see increased crop yields. Early stage trials that we've seen suggest median improvement in yields of about 13%. You see cost savings from farms as we get better at quantifying the release of the macro and micronutrients that the rock delivers into the soil. We can start drawing down some of the fertilizer that farmers traditionally put in their fields. That can reduce their costs. And that has a carbon effect as well. If we can avoid putting potassium and potash on our soils, those things have large carbon footprints that we would love to be able to avoid. And then from soil benefits, this process increases soil pH. So places that use lime can substitute at least a portion of their lime with the work that we're doing. We can release micro and macronutrients, and because the increased availability of those micro and macronutrients often help the development of a healthier soil microbiome, we often see a lot of knock-on benefits there, including increased soil organic carbon. So there's a lot of, I ran through that quickly, but in hopes of kind of describing that's the scope of why I think it's really cool. It absolutely can happen in the Hudson Valley. What needs to happen now are the education of farmers. It's really well placed in that there are a lot of people in the Hudson Valley that are interested in regenerative ag. And there are a lot of, farming communities that are ready to kind of get into alternative sources of income, better ways of integrating with the wider carbon market, kind of reducing dependency on fossil fuel derived fertilizers. And, in addition to that, as Chris says, a lot of these technologies are really new. So we need to build trust on the farm side. We also need to build trust on the carbon market side, ensuring that people have confidence that what we're doing stores carbon durably long term, as we're, and we can prove that scientifically. And then, practically access to rock. There's less volcanic rock in the Northeast for practical reasons, or for geologic reasons, than in places like the Pacific Northwest. But there are areas of rock that could be used for this kind of work. And then setting up and scaling pilot operations so farmers can feel comfortable with this kind of work in the same way that we have done in Scotland and other parts of the US.
Yeah, that was what I was wondering, if you had looked into where we can get some of the material to do ERW in the Hudson Valley. Well, I did see Silicate in Ireland, and they were doing waste concrete,
Yep.
which I think is very suited to this region, given all the concrete production along the Hudson. So just putting it out there, guys, that we can do ERW with waste concrete.
Yep.
And there's a process there, but it's fascinating. And again, gets rid of a lot of waste that sometimes ends up in landfills. When those trucks show up and they rinse them out, all of that goes back to landfill. It doesn't necessarily get used. You can use that for ERW, and it's great for fields that are doing tests now, and it is coming back really nice in terms of the data. So I guess I'm going to move on to Dita, because she's also in ERW and also in education. Dita, you're part of the founding team of Carbon Gardener. I have had a little bit of experience with you guys. It's a new citizen science project that is looking to launch in the Hudson Valley. Can you tell us a bit about what you're trying to do and what it is that you're solving, what problems you're solving? And you're also the youngest member on our panel, attending Cornell University next year. What got you so excited about what you're doing? So two-part question, what are you doing and why are you doing it?
Awesome. Yeah, I just want to start off by thanking Chris, Layla, and Melissa for having me. But yeah, Carbon Gardener is a citizen science initiative to scale up and diversify the field of data collection for enhanced rock weathering, and see how efficient it would be in carbon removal in soil. So when we're talking about enhanced rock weathering, in our case, I know Peter explained it really well, but the rock dust we'd be using would be like basalt, wolstenite, olivine, and we'd be spreading this rock dust over a large area of cropland. And that can improve the agriculture performance by adding micronutrients, which is like higher crop yield, but it also increases the pH. And that's where the carbon capture part of it comes in. So by increasing the soil pH, we convert the carbonate, the carbon dioxide in the soil into stable bicarbonate and carbonate. And that's how it's stored for 1,000 years. And we know that this is accessible. We know it works. We know it's cheap. We know it's modular, meaning you can change out what rock dust you're using based on what area you're in. But what we don't know, and what gap Carbon Gardener aims to fulfill, is how rock dust impacts soil chemistry and how to actually measure carbon removal, which is MRV in our case. So what we do is we reach out to universities and we're like, hey, we'll send you a test kit. You guys already have the measuring devices, which is like titrations, lysimeters, and you'll create a soil bed and you'll spread our rock dust on it, and you'll do a year-long test on, the soil chemistry, and you'll report it live to us. And it's super low cost. And at the end of the year, we're hoping to gather all that data, publish it open source, and just have more data to show to investors that this is a viable idea to add to the carbon tech and carbon capture list of things we have to do. And then on what got me so interested in carbon tech and the Cornell thing, I think I joined the climate space back when I was 15 with Chris. I was always super interested in what I could do that's tangible and profitable and sustainable long-term for my career goals. And I think carbon tech really aligned with that. And also just the testing that we're doing is just so cool. And just being able to show up every day and see real time, watching data and carbon being captured on graphs and knowing that I'm making an impact is really awesome for me. So that's what got me into it. Yeah.
I think it's great that you have a project that engages other people, so what I like about where we're at is a lot of this stuff is doing while learning too. So you can engage other communities and doing enhanced rock weathering and learning about how it's working in real time. So it's not just lab software, staring at a screen kind of work. It's engaging people and getting their hands in the dirt literally to do what you're doing. I will move on, and then anyone who has questions, please you can raise your hand in the chat or put them in the here, and I'll integrate it. But I'll include now Josh. Josh, you're a chemical engineer by training, and for the Bioenergy Consortium at the National Renewable Energy Lab in Colorado. You are focusing a lot on research and deployment of BECCS, bioenergy, carbon capture and sequestration, carbon removal and storage through biomass, or BICRs. Can you tell us what these things are? I love their acronyms. I have to say the CDR has a ton of acronyms, and BECCS and BICRs has the best ones, I think. And do you see any hope for us here in the Hudson Valley for this kind of work?
Yeah, thanks. I'm happy to be here, and thanks for the invitation to join this panel. And And I think Chris and Layla, you guys both hit on one of the challenges already with this field is just the amount of nomenclature and some of those pieces that are changing rapidly over time. And this is one that has changed recently. And so in both of these cases, so one is BECCS, which is bioenergy with carbon capture and sequestration. And one, depending upon how you pronounce it, I call it BICRS, biomass, carbon removal and storage. So they both start with biomass, and they're both carbon removal or carbon negative technologies. The key difference is BECCS is focused on predominantly initially, that more of the focus is on energy generation with sort of the CO2 capture and removal as a secondary emphasis, whereas BICRS is focused solely on the carbon removal piece. And you don't necessarily need to generate energy. And so the first one, you might try and say, take biomass, maybe burn it, combust it, and create heat and electricity as your energy. And then you would capture the carbon dioxide generated and store it underground. Whereas a BICRS approach may be similar to what was talked about before with Bill, where maybe you produce biochar and you sequester that in the soil or underground. There's other avenues where you can produce bio oil and actually inject that underground. And so they're two analogs. It's just a difference of focus between one has a bit more of an energy focus. The other one is more using the biomass for its carbon removal potential and value primarily, which is the BICRS space. I think absolutely there's an opportunity space for the Hudson Valley region, given that predominantly this depends upon local agriculture and depends upon local forestry, because you're looking at various waste streams coming from those practices, or even targeted grown crops for those practices as your feedstock. And so in these regions, you have access to local forests, you have access to local agriculture, and I think that really sets the stage for being able to do this type of processing. And Peter already alluded to some of that in terms of the scale of which you have access to those front end large industries already today.
And how much material is necessary or needed to do this work? I mean, is the flow of the material to do this work available in our region?
Yeah, I'm not sure I have the details on sort of the availability of feedstock in the Hudson Valley region, but this can be fairly dependent. It actually can be scaled pretty readily. Often these units are sometimes even built on skids or on the back of tractor trailers and can be deployed out into the forest. So, we deal a lot with this with Colorado with forest fires and the need to do forest thinning. And in some instances, they can actually take these units out and do, let's say, pyrolysis as an example, heating up the biomass to make char or make a bio oil out in the field, and then can transport that to a storage site. It is readily scalable and in sometimes deployable sort of in units and in steps, as opposed to thinking necessarily of like a large facility.
Amazing. And I know that that BECCS and biochar and BICRS, I always said BICRS, I guess, because I'm online a lot and not talking about it, those, if you look at those graphs with Chris had showed the green part when we're going below that blue line, a large part of it in the early stages is biochar, BICRS, and BECCS. Mm-hmm. Where are we with scale across the country, and how can I really do feel our region can start leading in this space? What do you think?
Yeah, absolutely. I mean, I think the scale of movement today is still quite small across the US. If you look at sort of projections for the United States in terms of availability of biomass resources, there's a study that's been put out by Department of Energy that suggests we can get to 1 billion tons of sustainable biomass resources across the US. Some of that is in targeted energy crops. And I would say much of those feedstock supply streams are not yet established well, outside of a few areas where if you look at like in the Southeast, where we already make wood pellets and ship those to Europe for their wood-fired energy generation, that's a place where there's some of that supply chain stood up. I think there needs to be an emphasis on that front-end logistics and supply chain aspects to build this out and go up in scale. But nominally across the US, our scale potential is quite large if we can establish those supply chains.
Terrific. And I'm going to integrate a question. Someone wants to know regarding biochar, what is the difference between charcoal and biochar?
That's a good one. I get that one a lot. So charcoal would be a kind of biochar. It's generally made from hardwood. But the difference really is that, charcoal is meant for fuel to burn, and biochar is meant to hold and sequester that carbon. So if you burn biochar, you're basically taking away its carbon capture ability and value.
That's very straightforward. Let's see. I'm seeing another question come in. One critique from the environmental community is of scaling production in one place and shipping to another, which can be considered an extractive practice. Thoughts? And I'm just going to throw in MRV, as Chris had said, monitoring, reporting, verification. Part of what makes good carbon removal is that they take these things into consideration. A lot of things do occur in the same spot, but I'll throw it to the panel. Who wants to take up this idea of moving things around to do this work?
I can take this question from like an ERW perspective, just because this is something that we do think about. Like if we say that we're doing enhanced rock weathering and we just say that we're using basalt, and basalt is only available in let's say Texas for some reason, and we have to ship it all the way here, that's releasing a lot more carbon than we would be capturing in a very short amount of time. So a big part of enhanced rock weathering is making sure it's modular and finding which rocks are available to make rock dust in specific areas and specific climates, so we don't have to ship it and fly it over. And that's just a big part of taking into consideration what's modular when we're designing our experiments and stuff.
Yeah. Peter, do you want to add anything to that?
Yeah, that was, I think, really well put, Dita. I think for context, we generally operate between the 25 and 50 mile range from the source of the rock to the application of the rock, because of the LCA, the carbon accounting that we need to do. The driving at really, really long distances is something that both doesn't make sense from a carbon perspective, but also doesn't make sense from an economic perspective. So those financial and environmental pieces tend to be aligned, at least with enhanced rock weathering.
And I would tend to say, in general, the CDR industry, because it is trying to address this issue, first and foremost looks at the supply chain, the value chain of all of this, and the carbon calculating is quite extensive. So, but yeah, it's a good question, and we are thinking about it. I have a larger question about, again, one of the reasons why we called this meeting is to do outreach and education for the specific region. And we had thought that this region, given the land, given the weather, given the resources, that that BECCS, that biochar, that ERW would be good. Could we talk about scaling here? What are the steps that need to happen in your mind, and throwing it to the panel, that we have to undertake in this region to start doing this work at scale? Does anyone have any thoughts?
I'll take a stab at that, I guess.
I have but I would go ahead.
Go ahead. Well, I mean, I think for one, basically every municipal transfer station should, in my mind, have a pyrolysis system set up. I mean, we shouldn't be shipping around, moisture filled waste biomass all over like we do. And it's particularly, in Ulster County where I am, we ship halfway across the state a lot of our trash, and it's crazy. And they have set up a compost program, which is great, but there's still a lot of material that is contaminated and is not available to be made into compost that could very easily be made into biochar. And some of the other co-benefits are it can destroy PFAS, it can destroy pharmaceutical residues, like that. Process of pyrolysis is could really help. There's a lot of co-benefits, there's a lot of additionality that can happen with that. And I think part of the problem is people, and I think maybe this was later, but one of the main drawbacks, I think, is people think that pyrolysis is is the same thing as incineration, and we need to and there's some regulatory sort of hurdles around that, convincing people and showing them that when you heat something up is different from burning it. And I think that's but there's a lot of opportunity, like, all these, municipal transfer stations that are already set up. The infrastructure is there where people are bringing their stuff locally, and those could become all, regional pyrolysis stations.
As we continue to talk scaling, I now have a bunch of questions in the chat box, but I will say that from where I sit, I think what we need to do in the region is map the resources that we have for the feedstocks for these things so that we understand what's where. And I think Melissa has been talking about that and also aggregating who's already done that work in other areas. So there's sort of an aggregation of information where we need to understand what is where in this region, and also regulation to make sure that there's a CDR framework for the Hudson Valley region so that some of this work can proceed, because I know biochar is running up against some issues because of the heating versus burning concerns and things like that, and also trucking or whatever it is. So there's that, but I will turn to a couple of questions here. I think Kate Butler, I think that Bill may have just answered your question, but her question was, when you use animal manure for biochar, substances such as bacteria, protozoans, herbicides removed or destroyed during the process, Bill?
Yes, that's correct. Yeah.
So everything gets burned off. And then let's see, we have a question around how do you pronounce that? Wollastonite? Peter, can you
Wollastonite, yep.
Wollastonite? Yeah. What is that?
Yeah, so I can just speak to this quickly. There's a relatively large reserve of wollastonite in the Northeast Adirondacks. And I think these are the kind of deposits that can be really useful in the context of enhanced rock weathering broadly. Like you're saying, you can do it with a lot of different minerals. The reason that we as a company haven't specifically gone after that opportunity is because it's logistically complicated. We operate with agricultural application in mind. So you need to be near agricultural centers in order to do it. And we think about the relative scale of the work that needs to get done. So we want to optimize in places where we're able to do work that scales. For context, I think the Adirondack wollastonite mines have surfaced something like 30 million tons. Is that right? I think maybe it's less than that. No, it's only 6 million tons. So those numbers are very exciting and would represent a huge step forward for the CDR community, but are challenging to execute against opportunity. So I think there are lots of kind of balancing that we need to do as we evaluate these opportunities in the Northeast.
Okay, terrific. I have another question. Then Melissa's raising her hand, but Simon had asked. Simon Gruber has said, "How much potential do you see in mass timber as a way to hold carbon for decades or longer, in structural timber or finished materials in large and small buildings? The recent New York State climate planning process included discussion about New York State's hardwood forest resources is useful for the finishing materials trim cabinets, but less relevant for the larger structural members being used in the high rises now." Is anyone able to answer that question on carbon storage inside buildings?
As a woodworker and working with woody biomass, I guess I'll take it. I'm not a professional in mass timber, but I do think there's a great opportunity to store the carbon in wood as well. We've been making buildings out of wood for hundreds of years, and we should keep doing that.
Yeah, I think from what I know, it's not like the permanent carbon pool storage that you're dealing with. It's not the hundreds of thousands of years, but it's certainly for our bottleneck moment, good. So yeah. So
you can always make biochar out of it later.
Or you can exactly. Melissa.
Okay. Yeah, I just wanted to say at the top of the hour, we have 44 nerds on this call. Sustainable Hudson Valley is completely committed to following up the exploration, as Lila said, mapping out assets and materials flows and who's involved. And we will share the chat and the recording with everybody. I note there are people from county government, from climate commissions, people who are pretty knowledgeable about this stuff. So I think we've laid some fabulous groundwork, and I just can't thank Chris and Lila and the panelists enough. You're never alone when you work with Sustainable Hudson Valley, we like to say.
Terrific. Well, thank you, everybody. I think that there's a ton of links in the chat. And if you can reach out to me, Chris, Melissa, anyone on this or any of the I don't know, I want to offer the panelists, reach out to them anytime. But anyway, we're here to answer any questions. It's exciting. It creates jobs. It's what's coming. So I'm glad that you were all here to learn a little bit about it.
And thanks, folks. I'll be sharing, editing the video tonight and sending the links over as well to everybody who registered by tomorrow. So please share it broadly and let's get more people into the conversation locally.
Thanks, everyone.